All right, so we're going to talk about dynamic chemical equilibrium. If I could have your attention here, class. When a system is, ladies, I'm speaking now, so the world really needs to pay attention, okay? All right, so we've talked about rate laws, right? Rate law, rate expression. We've talked about the rate of reaction and how to calculate that given some data. Now we're going to talk about equilibrium. So you've heard the word equilibrium before, right? Lots of times when you're talking about, oh, I've lost my equilibrium, you feel like you're tipping over, you're dizzy or whatever, right? So your equilibrium is sort of the balance, right? You guys are a little out of equilibrium right now. Yeah, if you have vertigo, or if you're just dizzy, or if you're sick even. Like if you got a really bad head cold, I don't know if you guys know this, this is science related, right? You guys should know this, but you have like semicircular canals in your inner ears. And they're filled with fluid, and actually not quite filled with fluid. This fluid tells your brain if you're standing upright or if you're laying down. Yeah, so it's kind of like there's a little bubble inside these really intricate. So if the actual substance inside those semicircular canals gets affected, like if let's say if it gets thicker, like if you drink alcohol, you should not be doing that. But if you do, if a person does, okay, not you guys, if a person does, that affects their brain chemistry. It affects the viscosity or the density of the fluid inside these semicircular tubes, and you lose your equilibrium a little bit. You get thrown off just a little bit, okay? So, by the way, you should be off your Chromebooks. I do not want you looking up other things while I'm talking, okay? You can save it for later. Jot it down, save it for later. All right? So equilibrium is a balance. And when we talk about chemical systems, we're talking about a balance, kind of a forward, back and forth, sort of seesaw, teeter-totter balance. So when a system is at dynamic equilibrium, this means that the reactants are creating products at the same rate as the products are turning back to reactants. No. No, it won't be. Not anytime soon, anyways. You'll have to jot this down in your notebook. There is no measurable change even though things are changing constantly. Okay? The other important thing to remember with chemical equilibrium, when things are, reactants are creating products and products creating reactants back again, is that there is no measurable change even though things are changing constantly. So we're going to watch this little video here, and hopefully that'll give you an introduction to equilibrium, and then we'll move on to make calculations and talk about actual quantitative data and what we can calculate during equilibrium. All right, so we watched that little video on equilibrium. Now what I want to talk to you about is the connection between rate law and a special constant that has to do with equilibrium. So equilibrium, okay, quantitatively, that is numerically, number-wise, described as the point at which the rate of the forward reaction, reactants becoming products, and the rate of the reverse reaction, that is products disintegrating into reactants again, would be the same. The rates would be exactly the same. There would be no observable change, but we would have A and B producing C and D with a forward rate of, and let's say that both A and B contribute to the reaction rate, like we studied before. Let's say this is what we have. It's a single step reaction, so we have everything involved. And then you have the reverse rate, which has the arrow going the other way, and the reverse rate would look like this. Okay, does everyone kind of see that? Going forward, producing C and D here. So A and B are going to contribute to that, and here C and D are going to contribute to the reverse rate. So if the rates are equal at equilibrium, then we can write the forward rate law here, rate expression, equals the reverse rate expression. And another way to write this, okay, is to come up with a new constant. And this is what we want to focus in on here in the last part of this lesson. This is a new constant that includes both the forward rate and the reverse rate information. And this is called the equilibrium constant. And it's got a special notation there, Keq. So we're going to be looking at that quite a bit. So Keq, okay, I can't really erase that, but it's simply just like that, Keq. Now notice that we have a reversible reaction, so this is now A plus B is reversible, forward and reverse, and you'll see kind of a double half arrows like this for equilibrium. You'll see that a lot, and that's what it means. It means that the forward and reverse reactions are going at the same time. And so we always put whatever's on the right, those ones are on the top. And whatever's the reactants are on the bottom. And I know it's reversible, and I know really there isn't technically a forward and a reverse, but when we interpret what the equilibrium constant is as a value, it's going to give us some information as to which are the products, which are the reactants, and which one there are more of at equilibrium. Okay, so it is kind of important that the products always go on the top. All right. Okay, so the equilibrium constant. Okay, so here's another example here. Again, if you want to follow along page 561. The exponents. Okay, let's talk about the exponents here. In our forward one-way reaction, we kind of had to take data from a data table and try and figure out which reactant was included in the rate law, which one would determine. Well, if we have an equilibrium system, and it's just a simple sort of a one step forward, one step backwards, we're going to assume for these questions that we're doing in high school here that everything is involved. And as far as the exponents go now, the exponents are going to be very simply related to the coefficients. So the exponents for each species is the coefficient that's in the equation. Okay, so I'll get you just to kind of maybe write this out right here. The exponents in the Keq expression are the same as the coefficients from the balanced chemical equation. And we'll do a quick example. Let's do an example from your textbook. This is going to be the first question that I'm going to get you guys to do as part of your assignment. So let's do it together. Okay, so all right, so we have this equation here. This double arrows means it's in equilibrium. So in order to write the Keq expression, and notice there's no k's here anymore because both k's are actually wrapped up in this number right here. So we don't have to have a k in here like we did with the original one. There's no k in there. So the Keq, and what you do is you just list the products on the top, so CO2, and we're talking about concentration, so use your square brackets, concentration of, NH3, square brackets, and this is a coefficient of 1, this is a coefficient of 2, so what does that mean? Does that mean anything? Yeah, the NH3 is squared. Okay, and then over here we have concentration of NH2, COONH4, and you guys are going to look that up and name that for tomorrow. Tell me what that is. All right, it's one of our organic groups there. So, and this is a coefficient of 1, and I guess we didn't really look to make sure that this was balanced, but appears to be balanced. And so that's your Keq expression right there. Okay, that's the Keq expression. So in question number 10 in your textbook, that's what it's asking you to do. Write the expressions given the equations. All right. So that's where we'll end here for today, kind of part 1. You need to be able to write an expression just like that for today. And tomorrow we'll do some calculations with the KEQ. All right? So question number 10 is what you should work on for tomorrow. Finish number 10. Okay? Number 10 is your assignment for tonight.